Hello, I will now do the chapter for one of the chapter 5 review worksheets. So this is a nice summary of the main concepts we've learned in chapter 5. And so here we go. Let's do this. So the first problem says, the first context says 40% of zombies are enrolled in a dance class. Now, by the way, I've scanned this and put this in Schoology. Along with the solutions, along with the other chapter 5 review worksheet, which has very similar content to this. So if you want to print out the worksheets and also the solutions, you're certainly welcome to do so. All right, so it says 40% of the zombies are enrolled in a dance class. 34% of the zombies are enrolled in are capable of driving a car. 30% of the zombies are both enrolled in a dance class and drive a car. That is telling us there's a good chance Venn diagram is what this is. When you're given the probability of one thing, probability of another, and the probability of both, there's a good chance you make a Venn diagram and it'll make the problems a lot easier. If you randomly select one of the zombies, find the probability of that, and we got to find these probabilities. So let's make our Venn diagram first. So with our Venn diagram, so we are going to have the first the first variable is whether or not they join a dance class. The second variable is when they're capable of driving a car. So I'll put C for car. All right. And it says 40% are in the dance class. So I'll put 0.4 at the top of that, at the top of the dance circle. And then 34% can drive a car. So I put 0.34 at the top of the car circle. 30% are both. So that would be 0.3. Like that. So that's what we're given. And so whenever let me complete our Venn diagram, because I explained this more in-depthly in the chapter 5 section 2 video. So we'll subtract these two things, 0.34 minus 0.3, that's 0.04. That represents this crescent shape region, meaning those that drive a car but aren't in the dance class. So notice the two parts add up to the whole. You go 0.4 minus 0.3, that's 0.1. So that represents the people that are in the dance class, but they don't drive a car. And then on the outside is everybody else, or all the other zombies, which are those that don't drive a car and they also aren't in the dance class. And when you add these up, that plus that plus that, that adds up to 0.44. That's probably one or the other. So 1 minus that is 0.56. And so these four regions, this, and this have to add up to 1. So, and I believe they do. So now we can answer the questions that are being asked. What's the probability they are neither enrolled in a dance class nor drive a car? So that's 0.56. The notation for that would be they are not in the dance class complement, and they do not drive a car. And so that would be 1 minus the probability of either, 1 minus 0.44, and that is equal to 0.56. Right, like that. All right, what's the probability they can drive a car, but they are not enrolled into the dance class? Well, that would be this. They can drive a car. The probability of that would be 0.4, but we have to subtract off those that are in the dance class, 0.3. So, oh wait, I'm sorry, I looked at that wrong. Yeah, my bad. It's driving a car. I'm sorry, driving the car is 34%. Yeah, 34, so it's 0.34. So it'd be 0.34 minus 0.3, and that's 0.04. That is that group right there, 0.04. All right, they can drive a car given they're enrolled in a dance class. So that is from section 5.3. So, and number 3, so it would be probability. So for number 3, be the probability they can drive a car given a dance class. Okay, so our formula on our formula sheet for that is our second formula. These are the two formulas in chapter 5. This is the addition rule, okay, right there. And then this is the conditional probability rule. The probability of A given B is the probability of both A and B over the probability of the given, the second one. So it's the probability of both of those things over the probability of the second one. So in this particular case, this would be the probability of C and D, the overlap, over the probability of D, like that. And so C and D, so that would be 0.3 over the probability of D, which is 0.4, and so that's 0.75. And so there you go. So that's the answer to number 3. So number 4, they're enrolled in the dance class given they drive a car. So for number 4, what's the probability they're enrolled in the dance class given car? Well, once again, using that same formula, it's the probability of dance and car over the probability of car And so that would be 0.3 over the probability of car is 0.34. And that is equal to 0.8824, I do believe. So that's that. Number 5, they're enrolled or they're not enrolled in a dance class. The probability they are not enrolled in a dance class complement, given that they cannot drive a car, like that. Well, using that same formula, that's the probability they are enrolled in a dance class and they can't drive a car over the probability of car complement or they can't drive a car. Well, dance class and not car, that's the outside here. That's 0.56. Like that. Well, what's the probability of not driving a car? Well, the probability of driving a car is 0.34. So the complement of that is going to be 1 minus that, which is going to be 0.66. So it's 0.56 divided by 0.66. And so that, in fact, is equal to 0.84 repeating. So that's number 5. That's a bit of a tricky one there. All right. And so then number 6, show whether or not they're independent. Well, there's 2 things. You got to memorize how to show independence. One way. Now, you just have to do one of the 2, but you need to know both of them. If they're independent, okay, the probability of one times the probability of the other is equal to the probability of both D and C, if they're independent. So let's see if they are. We'll say 0.4 times 0.34. So is that equal to the overlap, which is 0.3? Okay, and so 0.4 times 0.34 is 0.36. That is not equal to 0.3. So therefore, D and C, always state the context, and that would be stated in context, are not independent. The occurrence of one is associated with a change in the probability of the other occurring. The other way of showing independence, that's one way, is to show that a conditional probability is equal to just the first thing. So if they're independent, the probability of D given C is just going to be equal to the probability of D. Doesn't matter whether C occurs or not, the probability of D stays the same. Well, D given C, we just found that to be, D given C, we found that to be 0.8824. So 0.8824. And the probability of D being in the dance class is 0.4. That is not equal to 0.4. Therefore, they're not independent. So, and similarly, you could say the probability of C given D, if they're independent, well, that would equal to probability of C. Well, C given D, we found that to be 0.75. And the probability of C is 0.34. They're not equal. Therefore, these events are not independent. They're not independent. They are influencing each other, in other words. So that is that. All right, context 2 deals with a two-way table. All right, so when you have a two-way table, the first thing, so this says the students at Haunted High were surveyed and asked what gender they were and what sort of creature they are. And here are the results. So you've got vampires, werewolves, and trolls, and you got males and females. So when you have a two-way table, the first thing is come up with the marginal distributions. In other words, add up the columns, add up the rows. So the total number of vampires is 155. Total number of werewolves is 118. The total number of trolls is 124. So the total number of creatures here, you say that plus that plus that. I believe that's 397. I hope I got that right. And so the total number of males, that plus that plus that, would be 246. And the total number of females, that plus that plus that, is a total of 151. Now we can answer the questions that are being asked here. All right, what's the probability you'll get a male troll? If you randomly select one of these creatures, it'll be a male troll. Male trolls, there's 112. Out of the total possibilities, 397. That's it. And that would be considered showing your work, and you don't have to oh, did I do that right? Male troll. Yeah, I did that wrong in my key. So darn it. But anyway, okay. So the probability of male trolls, definitely 112. Okay, good. So what's the probability they'll be male? Given troll, male given troll. Well, given they're the trolls, you can only look at what you're given. You're just given these 124. Well, if you randomly select one of those, what's the probability they're male? And that would be 112 out of 124, like that. All right. What's the probability they're a vampire if you know they're female? So that's the probability of vampire given female is what that's asking. So given, you can only look at what you're given when you have a conditional problem. Given you're looking at one of these 151 creatures, what's the probability they're a vampire? It'd be 97 out of 151. Okay. Show whether or not gender is independent of creature type. Now, if I can just show it for any one of these cells, it shows that any one of them are not independent. That means that all of it is not independent. So I'll just take like let's say with the male with the males and the troll. So let's say show whether or not they're independent. So if they're independent, the probability of being male times the probability of being a troll would equal to the probability of male and troll. That's one of our little independence formulas. So male, the probability of male would be 246 out of 397. The probability of being a troll is 124 out of 397. What's the probability of male and troll? Male and troll is 112 out of 397. And so let's see what those are equal to. So 246 times 124 is equal to, and then divided by 97, divided by 397. So I get that this comes to 0.1935. And let's see what this is equal to. So 112 divided by 397. And so that is equal to 0.2821. Those are not equal. They are not equal. Therefore, being male and being a troll are not independents, which means that gender and type of creature are not independent. The occurrence of one changes the probability of the other one. And specifically, they don't look to be independent, because if I told you they're female, they're more than likely a vampire. If I told you they're male, they're most likely, more than anything, to be a troll. So that means they're not independent. So, okay, good. All right, number 11, if you randomly select 3 of the students, what's the probability all 3 are vampires? So this is a multiple event. Remember, with a multiple event, you multiply. So we would say, first of all, what's the probability that the first one's a vampire? Well, there's a total of 155 vampires out of 397 creatures. That's the probability the first one's a vampire. Well, given the first one's a vampire, what's the probability the second one's a vampire? Well, now there's only 154 left. And there's only 396 creatures left, because I just took one out. Given that the first 2 are vampires, what's the probability the third one's a vampire? Well, now there's only 153 vampires left, because I just took 2 out, and there's only 395 total creatures. And so this, in fact, is equal to, according to my records, 0.058811. Not like that. So multiple events you multiply, but you have to take into account their conditional nature. The fact, now, if you're using replacement, in other words, if you were taking one out and then putting them back in after you recognize what they were, then it'd just be 155 over 397 cubed. So, okay, so that is that. So that takes us to the next context. So first two big types of problems, Venn diagram, two-way table. Let's see what this one is, context 3. So context 3 says 40% of participants in Dracula's Halloween party wore a superhero costume. If they wore a superhero costume, the probability they brought food is 0.84. If they did not wear a superhero costume, the probability that they brought food is 0.11. So those are conditional probabilities. And when you're given conditional probabilities, the thing to do is to make a tree diagram. So that's what I'm going to do. So 40% wore a superhero costume. So let's make our tree diagram. So 40% wore a superhero costume. So I'll put S for superhero costume here. And so 40% did that. So I'll put 0.4 for that. So that means 60% didn't. So that'd be superhero costume complement. That means it didn't happen. So given they wore a superhero costume, if they wore a superhero costume, the probability that they brought food, so I'll put F for food, is 0.84. Well, that means there's a 16% chance that they did not bring food, but they did not wear a superhero costume. For some reason, they were a lot less likely to bring food. So I guess they were less into the spirit, but so 11% of those brought food. So that means 1 minus that, 89% did not do that. So there's my tree diagram. Now I've got to find the probability of everything that can happen. And the way you do it is by multiplying the limbs, each of these limbs. So the first group of people are the people that wore superhero costume and they brought food. What's the probability of that happening? Multiply the two events. The probability of superhero and food is just going to be 0.4 times 0.84, and that in fact is equal to 0.336. Then the next thing that could happen is superhero costume did not bring food. So probability of superhero costume and did not bring food. Multiply the two branches to get there. 0.4 times 0.16, and that is equal to 0.064. Then what's the probability they did not wear a superhero costume and yet they brought food? So that would be 0.6 times 0.11. That is equal to 0.066. And then lastly, this should be complement, by the way, sorry. So the lastly wore a superhero costume, did not wear a superhero costume, and they did not bring food. And so that would be 0.6 times 0.89, and that is equal to 0.534. So more than half of the people did not wear a superhero costume, and they did not bring food. All right, so now I can answer whatever questions are being asked. The first of which, if you randomly select one of the party goers, what's the probability they brought food? Well, there's two events with food on them, here and here. These ones were in the superhero costume, these ones that weren't. And so in regards to number 12, you would say, well, the probability they bought food, there's two of them. And so you would add, you show the addition. So showing your work here would be showing the tree diagram and then showing the addition like that. And so that is equal to 0.402, like that. Number 13. 13 says, if you randomly select one of the party goers, what's the probability they wore a superhero costume given they brought food to the party? All right. What's the probability they wore a superhero costume given they brought food? So this is a reversal of a conditional. This is in essence a Bayes theorem problem because it talked about up here in the stem of the problem, if given there weren't a superhero, you see someone in a superhero costume, what's the probability they brought food? Well, it's going in the opposite order here. Given they brought food, what's the probability they wore a superhero costume? So we'll use our formula for our conditional off of our table. It's probability of both of those things, superhero costume and food, over the probability of the second one, the probability of the given. Okay, well, the numerator there, superhero and food, that is the top thing here, 0.336. So that would be 0.336. And then the probability of food, that's what we just found in number 12. So that'd be 0.402. And so that in fact is equal to approximately 0.835821. So that is how you that's how you do that. Number 14. So number 14 says, if you randomly select one of the party goers, what's the probability they didn't wear a superhero costume given they did not bring food? So what's the probability they did not wear a superhero costume given they did not bring food? Well, we'll use our formula again. That'd be the probability of both of those things, not superhero costume and not food, over the probability of not food. Okay. Well, this is one of the branches here. It is that. So it is 0.534. So that's our numerator here, 0.534. And then probably if not food, but that occurs twice. That occurs here and here, these two things that I have not circled, there and there. So this would be 0.064 plus 0.534, like that. And then when you calculate that out, that ends up being 0.89298. And that's how you do that. Number 14, that's number 14. Number 15, if you randomly select 4 of the party goers, what's the probability that all 4 are not wearing superhero costumes? All right, so number 15, we know that 40% are wearing superhero costumes, but this is saying what's the probability 4 people are not doing that? Well, the probability that one of them is not doing that would be 0.6. Okay, so because you have 40% that are wearing a superhero costume, it means you have 60% that don't. Now, the probability of that happening 4 times would just be 0.6 times 0.6 times 0.6 times 0.6. We aren't subtracting anything because we don't know the total number of people. So it's just 0.6 to the fourth power. So we're sort of assuming independence here, or assuming replacement here, or assuming an extremely large number of people here. But so that's how you do that right there. All right, number 16. So that's it for that context. All right, so 16, if you roll two fair six-sided dice, what's the probability that the sum is greater than 9, given that it's greater than 7? Well, we discussed in the video on section 5.2 the probability distribution for the sum of two six-sided dice. And here it is. The probability of rolling a 2 is 1 out of 36. The probability of rolling a 3 is 3 out of 36, 2 out of 36. 4 is 3 out of 36, and so forth. The most likely one is 6 out of 36, and then rolling a 12 is 1 out of 36. All right, so what's the probability you're going to roll greater than a 9, given that it's bigger than 7? Well, on these sorts of problems, what you would do is you're going to take the probability of that and put it on top, and the probability of that, put it on the bottom. Because if you think about it, using in essence, our little formula for a conditional, the probability that X is greater than 9, given that X is greater than 7. Well, using our formula, it's the probability of both of those things. The probability that X is greater than 9 and X is greater than 7 over the probability that X is greater than 7. But think about this. If I told you that something was greater than 7 and also it's greater than 9, what's the easier way of saying that? Well, it has to be just greater than 9 if it's going to be true for both of those things. So it's just the probability of X is greater than 9 over X is greater than 7. So you would look at that. So you would look at this and say, what's the probability that is greater than 9? Well, greater than 9 would be 10, 11, and 12. So you add those three up, 336 plus 236 plus 136. That adds up to 636. What's the probability that is greater than 7? Well, greater than 7, you would add up all of these. You would add up 536 plus 436 plus 336 plus 236 plus 136, and that adds up to 15. So when you add these, when you simplify these, it's 6 over 36 or 0.4. All right. Now, so number 17, if you roll 3 fair 12-sided dice, what's the probability that all of them have values greater than 5? Now, the thing about this is we're not taking their sum. We're just rolling 3 dice. We're not adding them. So let's think about one dice. If you have one 12-sided die, okay, so it could result in any number between 1 and 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, okay? And so what's the probability it's going to be greater than 5? Well, greater than 5 would be all these, okay? So that would be 1, 2, 3, 4, 5, 6, 7. So 7 possibilities out of 12. So the probability to be greater than 5 is 7/12. But what's the probability that that's going to happen 3 times on 3 different dice? It's 7/12 to the third power. It's 7/12 times 7/12 times 7/12. So, and that in fact is approximately equal to 0.198495. I like that. So that is thus the answer to number 17. So there we go. That's 17. Okay. And then lastly, we have this guy here. So this says 48% of ghosts in a forest are nice. 32% of ghosts make strange noises. 28% of the ghosts make strange noises and are not nice. So this is a Venn diagram problem, but there's a little trick here that you have to be aware of. Notice the overlap is not the overlap between nice and strange noises. It's the overlap between strange noises and not nice. So let's make our Venn diagram. So if we make our Venn diagram, so it says 48% are nice. So this one is nice, and this would be 0.48. And so then 32% make strange noises. So I'll put S for strange noises, S for strange noises. And so that is 32%. Notice this says 28% make strange noises and are not nice. That is this crescent shape region here. This crescent shape region is strange noises are not nice. So this is 0.28, which means the overlap here has to be that minus that, or 0.4. That was the little trick to that one that makes it different from the other Venn diagram problem. Then when you subtract these two, 48 minus 4, so that would be 0.44. Okay. And so that would represent people that do not make strange noises. And then the whole diagram has to add up to 1. So this plus this plus this plus that is 1. And so when you say that plus that, that'd be 48 plus 28. And so that in fact is equal to, so 48 plus 28. So that's equal to 76. So this whole thing in here, 76, so 1 minus that would be 0.24. So that plus that plus that plus that has to add up to 1. So what percent of the ghosts are neither naughty nor make strange noises? 0.24. 0.24. And then show whether or not they're independent. So if they're independent, that times that is equal to that. So if they're independent, 0.48 times 0.32, it would equal 0.04. And let's see if it does. So 0.48 times 0.32 is equal to 0.1536. That is not equal to 0.04. Therefore, being nice and making strange noises are not independent. They're not independent. That's it. Thank you for watching my video. If you have any questions about that, that's a really quick run through of a lot of stuff. But if you have any questions, I'd love to hear from you, and hope you just have a great day.